All right, stats, this is 11.1, our notes today. We're just going to jump right into an example and talk you through it. So what we're introducing today is something called a chi-squared test for goodness of fit. Okay, so here's our example. You know those M&M candies, right? Well, the company's customer affairs department says that the color distribution is not even. On average, the mix of colors will contain about 13% of the browns and reds, 14% yellow, 16% greens, 20% orange, and 24% blue. And we're going to create a one-way table. They usually give you this part of the sample bag of M&Ms. So in our sample bag, we had 60 M&Ms, and we divided them out into by color and put out how many of the M&Ms we have in each one. Okay, so this is categorical because we are putting the colors across each one of the columns. And then we're putting down what our actual counts are, okay? So there is no confidence interval for these, which is good news for the entire chapter, no confidence intervals, just significance tests. So here's what a significance test question would look like. It says, do we have convincing evidence to conclude that the company's claimed color distribution is incorrect? Okay, or they could say is correct, either way. So our null hypothesis, we're not really going to have to explain what our parameters here are because we're not doing means, we're not doing proportion. So we leave that part blank. We're going to go straight to the null hypothesis, and we're going to say the company's claimed color distribution for M&Ms is correct. All right, and then the alternative is that it's incorrect. Right, remember you're always trying to claim the HA. All right, you're trying to prove that the HA, that something has changed. All right, so on to phantoms. So we skipped P, we did H, we're on to our three assumptions. And hey, look, they're the same three assumptions as before. Notice that the third one is called large count rule, not normal. There's a reason for that. So as we're going through these, let's take a look. So random, the data came from a random sample. Cool. Next one, 10% rule. So we are picking from a distribution, right? And we're not replacing these M&Ms. So we want to make sure that the M&Ms that we select, which is 60 of them, is more than our total population of M&Ms. Well, I'm pretty sure there's more than 600 M&Ms. So we can assume there are more than 600 M&Ms in our population. All right, and then we're looking at large count rule. So in the large count rule, this one is a new one. It's still titled the same thing, but our check for this one is that the expected counts, okay, and that's a new word. The expected counts for each color must be at least 5. Okay, so we're going to have to show them that. We're going to have to show if there are 10 colors, we're going to have to show that our expected count is at least 5 in each one of the colors. Okay, so next thing we're going to do is we're going to create a table that looks almost identical to the original. We're going to relabel everything so that we know what everything is going to be called. Just a minor relabel, nothing major. Okay, we're going to call this was our observation, right? So this was observed, and this one is expected. Okay, so the expected basically says if I took those same 60, what should the distribution have been based on the percentages that the company told us? So they told us that the blues were 24%, so we're going to put in 24 times 60, and we get 14.40. Now, expected counts are totally fine to be decimals because they're just the overall average of that count. Our observed count should be whole numbers, though. Okay, so expected counts can be decimals, observed have to be whole numbers. Okay, so I'm going to even write that, whole numbers. Okay, and then this one can be decimal. Okay, so same deal with orange. What was our proportion that they said orange should have been? It should have been 20. And if we do 20 times 60, that is 12, exactly. If we do green, how much percentage did they say? 16% of the 60. Yellow should be 0.14 of the 60. Red should be, where's red? 13 of the 60 and 13 of the 60. All right, so I'm going to have to calculate these anyway, so let's go put this into the calculator. All right, so turning out my calculator, we're going to go put this in a list, right? May as well. All right, so my first list was my original count. Now I'm going to have to remember what each color those represent, so I put them in the same order as my paper. So you can see they match exactly, 9, 8, 12, 15, 10, 6. Okay, that's just list 1. In list 2, I put all the percentages that match with those different colors. So I have to look at my paper and say blue is the first one, blue should be 24, and I'm putting them in as a decimal. So then when I go over to list 3, I could go up to list 3 and I could just say, hey, what are we doing? On each one, we're doing 60 times whatever the percentage is. So up at the top, I'm just going to say 60 times whatever was in list 2. There are my expected counts. There's the 14.4, there's the 12.0. Continuing on, we've got 9.6, we've got 8.4, we've got 7.8 and 7.8. So the second grouping is basically what we should have gotten if the M&M candies came out like they were supposed to, right? So I can look at that and I go, okay, wait a minute. The blues, we're supposed to get 14, we only got 9. The oranges, we were supposed to get 8, we got 12. The greens, we were supposed to get 9.6, we got 12. So these don't look like they're very close, do they? Matter of fact, the closest one is probably the brown one, where they said we should have been getting about 7.8 and we actually got 6. All right, so we're going to turn that into a number eventually, but we first have to create the expected count table. So that's there. All right, so moving on then into our phantoms is next thing we're going to go for is what's the name of this? Okay, this is called a chi-squared test for, I thought I changed the color, for goodness of fit. Kind of makes sense, right? It's like how good of a fit was my sample based on what the company said. And then we're going to say we already said it's a test, goodness of fit test, and we're going to say because it's a test, right? We're going to do an alpha level. Let's set it at 0.05. Okay, and this is not pronounced like Chicago. It's pronounced like chi. How would I spell that? K-Y-E, kind of like that. Okay, so it's chi-squared. And the symbol for it is the Greek symbol chi. It looks like our variable x. So this is chi-squared. This is the exact same thing as a notation. And we're going to go and add up a whole bunch of stuff. So what are those things that we're going to add up? We're going to figure out how far apart was our observed and our expected. We're going to square it because we don't care if it was an overestimate or an underestimate. And then we're going to divide it over by the expected count. So I've showed you the first one. We're going to have to write out every single one of these. Yes, I did say every single one of these. So in our first one, it was 9 was on top, was the observed, and we were expecting 14.4. We square that, we put it under 14.4. Then we go to the next one, and the next one was 8 minus 12 squared over 12. And then we go on to the next one, and the next one after 8 is 12 minus 9.6 squared over 9.6. The next one is 15 minus 8.4 squared over 8.4. Next one is 10 minus 7.8 squared over 7.8. And our last one is 6. Minus 7.8 squared all over 7.8. And we're going to calculate each one of those up, and then we're going to total them all together. Okay, so if I go and total those all together, I could actually do this on my calculator, and I could just create another column. And then what would I need from this? I'd need to subtract, square, and then divide, right? So I could actually go up here and create a complete parenthesis set here and say, take my list 1 minus my list 3, square it, and then divide by my list 3. And it would fill in all of those values, and then I have to write down each one of those values, 2.025 plus 1.333. You get the idea. Okay, and then I need to find the grand total of this, so I'm still stuck counting this all. So I believe I can sum column 4, and you're like, Power, this is so much on my calculator, you gotta be kidding me. Let's see if I can go find sum. There it is, number 5, and I want to sum, I thought it was list 4, right? And I'm getting 10.180. 10.180. So there's my chi-squared score, okay? There is another way we can do this on our calculator. We still need list 1, we still need list 2, we still need list 3. But just like everything else, we can just go run the test, and the sooner the better, right? So we are looking at a test, but it's going to be under all the other stuff we've done. Crazy to think we've already done all that top stuff, right? So here's our chi-squared test and our chi-squared goth. That's goodness of fit. We want to make sure we pick that one. How do we know we have the right one? Is they're going to ask for 2 lists. If you accidentally pick the wrong one, it's going to ask you something about a matrix. And then you're like, whoa, am I in the wrong place? So for goodness of fit, here, let me pick the other one so you can see how crazy it looks. So if you just grab chi-squared, see how it'll say like this whole thing of like it's a matrix. Okay, so we want to make sure we pick the one that just shows us a list. Okay, so there it is, goodness of fit. Okay, and where is your observed stuff? That was in list 1. My expected stuff, that's not the percent, that's what was my expected count in that second table of values, that's list 3. And degree of freedom, how do I get degree of freedom? So degree of freedom is going to be, degree of freedom in this case is going to be number of colors minus 1. So it's the categorical, how many categories do we have? And in this case it was 6 minus 1, so that is a degree of freedom of 5. Okay, and then I can go and calculate it. And it will give me all the important stuff. There's my 10.18. There's my p-value, it's a 0.07. And then there's something at the bottom called contribution is what it stands for. All right, so again, it's right there. We can do all of our same stuff. The other thing I can do is we're used to doing calculate because it gives us all of our answers. But this might be one where it might be worth it for us to actually look at the picture of this one. So I'm going to tell it to graph. So instead of just calculate, I'm going to tell it to draw it. It won't give me as much information. Okay, so this little line is something from my y equals. This is what the graph looks like. Can you see that it is not a normal curve? It still kind of has a hill to it, but it's definitely skewed to the right. So I can see it's got my chi-squared amount, it's got my p-value. It just doesn't have that contribution line at the bottom. Okay, so I already know what to draw. So I have already drawn it for you over here. Okay, notice that before we labeled these when they were normal, we said normal. If there was a t-distribution, we said t-distribution. In this one, we have to say it's a chi-squared distribution with the degree of freedom, right? And then we go find where 10 is. It always starts at 0 and then goes uphill. So I find about where 10 is, right? Categorize it, call it chi-squared equals 0 here, call it chi-squared equals 10.18 here, color in to the right. So very similar to our other stuff. All right, next step, obtain a p-value. Well, we already know what that's going to be, but we have to write up the probability statement. So what is the probability that chi-squared is greater than 10.180? It's always a greater than, and we'll tell you why in a second. And then we're going to go look for, same as before, we have a chi-squared CDF. We're going to start it at 10.180. We're going to go up to infinity, and we're going to say degree of freedom equals 5. All right, and that's going to give us our 0.070. And again, if I wanted to double check that, there is a way to do chi-squared CDF. Same spot as before under distributions. There it is, number 7 and number 8. We want CDF. So we would say start at 10.18. Yep, 10.18. And go up to infinity, so 10 to the 10th. Degree of freedom is 5. And there is our probability amount. All right, so because our p-value is, here we go with our usual stuff, because our p-value is 0.070, and it is, how does it compare to our alpha level? It is greater than, we would fail to reject HO. Okay, fail to reject HO. Our same summary types of stuff. That has not changed. So summary, if we're failing to reject, we do not have convincing evidence to conclude that whatever our alternative hypothesis was. So the company's claim color distribution for M&Ms is incorrect. So we don't have enough proof to say, hey, we think that their distribution is truly different. All right, that's it. That's not bad, right? That's pretty cool. All right, a couple other things to just notice here. Chi-squared, if everything matched, would have been a 0. So there's no way to get a negative number. 0 would be a perfect fit between the observed count and the expected. So the bigger the number, the lower your probability, the further right you're going to be. Does that kind of make sense? Okay, so the last thing we want to do is just kind of talk about a couple key points. Make sure your large count check is on whole numbers. Wait, make sure your large count check is on expected counts, not on observed counts. We don't care what we actually collected. We need to make sure, just like we did in proportions, that there's at least 5 in every group. So that's the expectation, that there's 5 in every group. Okay, expected counts can be decimals, observed cannot. If a problem states that the expected count is evenly distributed, then all I would do is I would keep all of those percentages the same. If there were 5, they're all 20%. If it's 4, 25%, right? Get the idea? Okay, do not draw the chi-squared curve like a normal curve. It is not a normal curve. They are all skewed right. And I've given you a picture of some of the different degrees of freedom right below this. And the p-value is always to the right of that chi-squared amount. That's the part you color in. Okay, so you'll notice when the degree of freedom is very, very small, it doesn't even look like it has a hill. Right around 2, it switches to the hill, and that hill starts out with that hill, the peak of that hill being really close to 0, and then it starts moving over and flattening out the further out it has to go. All right, so follow-up analysis. This is what that contribution did, is what if they asked you, and you don't fill this in as part of phantoms unless they specifically ask, what if they asked, what contributed most to your chi-square score? We had a 10. What counted for all of that 10? Remember that contribution amount. Contribution amount. So let's go run the test again. Good thing it's all still in there. I'm just going to hit calculate. And notice at the bottom it gives me 2.025. And as I arrow over, I have to remember what color is what. So I've got a 2, I've got a 1, right? And I can also go back to my original up here where you write down every single number and you can see which ones are the highest. I'm going to cheat a little bit here. You don't have to do this. I'm going to go back to my lists and I'm going to make my last list appear at 5. I'm going to go tell it to go find that contribution file. So remember, just like there's a resid file, there's a contribution file too. So it's under second list. See it at the bottom? All right, and there it is. So now I can see which one's the highest. It was this 5. It was the 4th one over. So the 4th one over, 1, 2, 3, 4. Yellow was the biggest contribution, it looks like. Double check. 1, 2, 3, 4. Yellow, and then the first one. So yellow was by far the most. That was the one that went from 15 to 4, right? So we can say that they were yellow and red. And then they want to know how much, like how much did it contribute? So the yellow contributed 5 out of the 10, almost half of the chi-squared amount came from the yellow. And then the red, there was about 2 out of the 5, 2.025. Cool. All right. Also notice it was right before us on line 4 when I calculated it out. You don't have to. And you can always just do it by hand with a calculator if you had to. A little bit tedious, but it gets it done. Last thing I want to show you is what happens to the degree of freedom. I've already shown you the picture. Let's talk about what happens to the probability amounts and then we're done. Okay, so to understand how degrees of freedom works, we're going to use a chi-squared is greater than or equal to 5, and we're going to compare it with a degree of freedom of 3, 5, 10, and 20. So I'm going to go out here to chi-squared CDF number 8. And I'm going to tell it to start at 5 and go up to infinity. And I'm going to start with a degree of freedom of 3. I'm just going to write down what that amount is. So this one is 0.17. If I go back and repeat that, and now change it to 5, what happens to the probability? It is now 41%, 42% almost. If I go back and I change it to degree of freedom of 10, it's now 89%. Oops, I did those wrong, got it. 17 goes here. 41.6 goes here. 89 goes here, and then our last one at 20, let's see what that turns into. So if I go and do 20, we get 99 or almost 100%. Why is that? Well, remember how we showed that the curve, that peak of the curve keeps moving over more and more, the larger the degree of freedom. So if we're going to stay at the level that is 5, if I'm going to stay right here, right? When I'm looking at the black curve, the lowest degree of freedom, there's very little under here. And by the time I'm at an 8, there's quite a bit, more than 50%. So what's the trend? As the degree of freedom increases, the p-value also increases or has more variability. Okay, and that kind of makes sense. If you have more categories, you'd have more variability. All right, a little bit long today, but hopefully that makes sense. We'll practice this some more later.